The second question from the take-home quiz is up on the board here. F of xy is x squared minus y squared, and we're working on the solid unit disk. Our function's continuous, our region is closed and bounded. The extreme value theorem assures us that we've got an absolute max and an absolute min. Now, that means, in general, we're going to have to check critical points and boundary points. Because my region is described as an inequality, I know that on the interior points, which is where the less than part would be satisfied, I might have some critical points that are the location of a max or a min. On the boundary, that would be where x squared plus y squared equals 1. I'm going to check that too. This problem specified that the way we're supposed to check that is to use the method of Lagrange multipliers. So I'm going to view that as a level curve for a function that I'm going to call g of xy. Very important, Lagrange multipliers only applies on the boundary, which is given by an equation. When we get to that, we're going to be setting up a system of equations. Some of you included an inequality in your system of equations. Inequalities don't belong in systems of equations. And the inequality describes the whole disk. Lagrange multipliers only applies on the circle. Okay, let's find our critical points first. So the gradient of f is f sub x, f sub y. That's just 2x negative 2y. Always defined, so no critical points from the gradient being undefined. The gradient of f would equal 0 if 2x is 0 and negative 2y is 0. So that just means x is 0 and y is 0. That puts us at the origin. That's definitely in the unit disk. So I'll put that up here. And at the origin, f will evaluate to 0. All right, on the boundary, we're told to use the method of Lagrange multipliers. Okay, so the gradient of g is g sub x, g sub y, and that's just 2x, 2y. That would be 0 at the origin, but I don't care because the origin isn't on the boundary circle. Okay, so this is never 0 on the constraint curve. We can use Lagrange multipliers. So we're looking for places where the gradient of f is lambda times the gradient of g. I'm going to use that together with my constraint equation to come up with a system of equations. I'm going to then need to show that I've considered every possibility and found all solutions. And to find a solution to a system of equations, you need to show that you can make all of the equations in that system true. That's very hard to do if you don't write down the equations. If you are doing Lagrange multipliers, it is a necessary step that you explicitly write down the system of equations that you're solving. Okay, so I'm going to just write that up in this corner of the board here because I'm going to keep referring back to it. I like to number my equations to make it easier to refer back to them. And I just start by saying this would be 2x negative 2y equaling lambda times 2x, lambda times 2y. So for my first equation, I'm just going to set those first components equal to each other. 2x equals lambda times 2x. For my second equation, I'll set my second components equal to each other. Negative 2y equals lambda times 2y. And then my third equation is the constraint, x squared plus y squared equals 1. All right, now that's a system of 3 equations in 3 unknowns. A solution is a triple of values, an x, a y, and a lambda, that make all 3 equations true. It's not a linear system, so I can't just attack the whole thing at once. I'm going to have to consider various possibilities or various cases. And here's where a lot of you struggled. A lot of you got to the right answer, but you sort of jumped around and pointed out various things. you didn't make a convincing argument that you had considered all possibilities, and you didn't demonstrate that you had satisfied all three equations. So, to make sure that I've considered all of the possibilities, I'm going to break this up into cases. My strategy, unless I see something else that looks good, my strategy is always to try in the first few equations that have a lambda in them to solve for lambda and to look at what could go wrong. What would keep me from being able to solve for lambda? Okay. Once I've exhausted all of the things that can go wrong, then I look at the nice case, what if nothing goes wrong? Okay, so this could go wrong, that could go wrong, this could go wrong, nothing goes wrong. Those are sort of going to be my cases. And depending on the system, that'll determine how many cases I have. Okay. That's not the only way to break things up into cases, but I kind of like it because it's a unifying strategy that works almost all of the time with these. Okay. So, if I wanted to solve for lambda in equation 1, I would want to divide by 2x. What could go wrong? X could be 0, and I know I can't divide by 0. So case 1, x is 0. Now that's all I'm going to write. I'm not going to make any assumptions about y or lambda, which are my other two variables. Okay? Because the more assumptions I make, the more cases I'm going to have. If x is 0, this is going to cover every single possible point that has x being 0, whether y is 0 or not. Okay. So now I just need to go through my equations. So I'm going to start with equation 1. If x is 0, and I just plug that in for x, it becomes 0 equals 0. It's very easy to demonstrate that in case 1, equation 1 is true, but I need to write that so that I know that equation 1 is true in this case. Now, there's nothing that says I need to look at the equations in order. Equation 2 doesn't have any x's in it, so I'm going to skip it and go to equation 3. And when I plug in 0 for x, that gives me 0 plus y squared equals 1. Y squared equals 1. Y is plus or minus 1. I don't want to stop here. I've got an x and a y, which is great. That's all I need to have a point. But I have not demonstrated that I have a point that's part of a triple that makes all three equations true, because I have only looked at 2 of them. So now I need to go to equation 2, and this gives me 2 separate possibilities. So these are sort of subcases, but now I can look down here at equation 2. I'm in case 1, so x is 0, and this subcase will be y equals 1. This subcase will be x equals 0, y is negative 1. If I plug into equation 2, this becomes negative 2y. I'm sorry, I'm plugging in 1. Negative 2 equals lambda times 2. Lambda would equal negative 1. Great. I don't really care what lambda is. It's not going to make it onto my table. But I care that there is a lambda that will make that third equation true, so that I've looked at all 3. Here, I'm replacing y with a negative 1, so that's going to become 2 equals lambda times negative 2. Again, lambda's negative 1. Either way, I can make equation 2 true, so I've looked at all 3. I've got 2 points, 0, 1, 0, negative 1. Excellent. So now, that covers everything that could go wrong if I try to solve for lambda in equation 1. Looking at equation 2, what else could go wrong? Well, y could be 0. Okay. Now here, I think I'm going to start with equation 2. If y is 0, equation 2 becomes 0 equals 0, so it's true. I'm going to go to equation 3, because that's the other one that has some y's in it. This becomes x squared plus 0 equals 1. X squared equals 1. X is plus or minus 1. So again, that's going to be 2 possibilities. So 2 sort of subcases. So I've got x equals 1, y equals 0, or x equals negative 1, y equals 0. But now I want to look at equation 1. The one I haven't looked at yet. So if I plug in 1 for x, it becomes 2 equals lambda times 2. Lambda is going to equal 1. If I plug in negative 1 for x, it becomes negative 2 equals lambda times negative 2. Again, lambda is 1. But with either of these choices, I can make equation 1 true, so these points belong on the list. 1, 0, negative 1, 0. Excellent. So that was me being pessimistic. What could go wrong if I try to solve for lambda? Well, I do actually have to consider the case that nothing goes wrong. So case 3, x isn't 0 and y isn't 0. So in equation 1, now I can do what I wanted to do from the beginning. I can solve for lambda by dividing by that 2x. Lambda equals 1. In equation 2, I can divide by the 2y. Lambda equals negative 1. It's got to be the same lambda. So I set the results from both of those equal to each other. 1 equals negative 1. That's a contradiction. Now with a contradiction, it does not matter that I didn't look at equation 3. If it's not possible to make equations 1 and 2 both true, there's no way to make all 3 of them true. So here I have looked at all possible cases. Okay, so turns out when I plug things in, these 2 points give me a negative 1, and those 2 points give me a positive 1. So I can phrase my answer as f has a min of negative 1. That's the value of it, and it occurs at 2 points, 0, 1, and 0, negative 1. And then f has a max of 1, and it occurs at 2 points, 1, 0, and negative 1, 0. So there's my answer. Okay. Now, I want to just show you how some other people approached this and talk about a correct way to take a slightly different approach from what I did, and then an incorrect way. Okay. So a lot of people started with equation 1, and they actually just subtracted that over to say that's 2x minus lambda times 2x is equal to 0. And then you can factor. So you can say 2x times 1 minus lambda equals 0, which means either 2x is 0 or 1 minus lambda is 0. So x would equal 0 or lambda would equal 1. Okay. Now, to make equation 1 true, one of these things has to be true. So if you took this approach, you only have to consider 2 cases. Case 1, x is 0. Case 2, lambda is 1. Totally fine. I did 3 cases. Here's a way that you could do 2 cases. But what you need to do, if you're going to do it that way, is write down your case and then within each case work through all of the equations. And what I saw a lot of people doing is jumping around. Okay, to make equation 1 true, these things have to be true. Now let's go to equation 2. But let's not suppose that we're doing this or this. We just know one of them is true. I don't know which one. To make equation 2 true, you can show that either y is 0 or lambda is negative 1. But if you write that down, I see 4 possibilities. X is 0, lambda is 1, y is 0, lambda is negative 1. I don't have to consider all 4 possibilities. I can consider just these 2, but I do need to, within each of those possibilities, work my way through all of these equations. If x is 0, when I move to equation 2, if I let y be 0, that would lead to a contradiction in equation 3. If lambda is 1, and I go to equation 2, if I were to let, well, if lambda is 1, then lambda can't be negative 1. So y would have to be 0. So I can see that there's a connection between them, but I want to show that connection. So once you've said, I'm in this case, stay in that case until you've either found a point that satisfies all three equations, so that would be a point x, y, and there's a lambda value that we don't care really what it is, but we know it exists. Or you reach a contradiction, or you determine that any points you might get are already on your list. Okay. All right, excellent.